Some practical situations need to be precise. They need to have as little variation as possible. For example, a machine that consistently both overfills and underfills a mold is going to have a mean that looks correct, but it's still going to be producing a lot of potentially defective parts. So to pin down the variation in a process, we need to be able to construct a confidence interval for its standard deviation. But there's a problem. Unfortunately, the sample standard deviation is a biased estimator. And remember, we're always looking for an unbiased one. Now, fortunately, if we take one step back and look at the variances, remember the variance is just the standard deviation squared, then we're back on track, right? The sample variance is the best point estimate of the population variance. All right, so to talk about confidence intervals for the variance and by extension, the standard deviation, we're going to need a new distribution. Now, suppose we take a really large number of samples from a normally distributed population where the sample sizes are all 5, right? And where I know the mean and the standard deviation, right? Now, I could have picked any sample size here, but 5 is going to work well just for an example. Now, suppose I calculate the standard deviation for each sample, and then, again, just using this as an example, I compute this expression and display the results in a histogram, right? And I've got that here. I've smoothed it out into a continuous curve, right? But this shows you how those values would be distributed. It would look something like this. And this is what we call a chi-square distribution, right? That's this symbol up here. This is the Greek letter chi squared. Now, the notation that you see here is a little unfortunate. Okay, like I said, the x is the Greek letter chi, which is fine, but the 2 isn't really an exponent. It's kind of a reference to the 2 squared values that you see over here. So when you see this chi squared in an expression, don't try to simplify it by taking its square root and just get the chi by itself. All right, that's not what it means. It's kind of just a label. All right. So if you like formal definitions of things, right, this is how our chi-square distribution is defined. Now, the key points you need to take away are that the underlying distribution has to be normally distributed. Right, now notice that there's no exception here based on the sample size, like we've seen before. The original population has to be normal or we're just out of luck. Right, and we've got this formula here. Right, that's going to be useful later on for turning a statement about the variance into one about the actual standard deviation. So before we go on, I want to highlight some key properties of this distribution. Now, on the right here, I've graphed the distribution for several different degrees of freedom, so you can kind of get a general idea of its shape. Now, the first thing you should notice is that the distribution doesn't have any negative values. And obviously, it's different for different degrees of freedom. Now, as we saw with the t distribution, this distribution becomes approximately normal as the sample size or the degrees of freedom. Remember, degrees of freedom is just the sample size minus 1, right, as the degrees of freedom increases. And you can kind of see that happening here, right? This really high-peaked graph, that has the smallest degrees of freedom. Then when I went up 1 to 5, it kind of flattened out. And then when we get here to 7, you can see it is kind of starting to take on that kind of distinctive bell shape. All right, finally, and again, you can see this in the graphs, the distribution, unlike the t and normal distributions, is not symmetric. This is going to cause us some challenges when we try to calculate confidence intervals. The symmetry of the other distributions meant that we could use the same z-score to determine both the left and right sides of the interval. The margin of error was the same on both sides. Right? We're going to have to work a little harder to get to the same point here with our new chi-squared distribution. All right, so just like with the mean and population proportion, we're going to need to find the critical values associated with a given confidence interval. Now, with our chi-squared distribution, we're just going to need to get two. We're going to need to get different ones for the left and right sides. So what I've got here in the upper right is part of a chi-distribution table, chi-squared distribution table, which is very similar to the t-distribution tables we saw earlier. All right, the first column lists the degrees of freedom, and the first row lists the probabilities. These are the 1 minus alpha values, right? Those are our confidence levels, if you will. Right? Now with a chi-square table, the values in the body of the table are always going to give you the area to the right of the given value. For example, for a distribution with 9 degrees of freedom, right, 95% of the area or the population is to the right of 3.325. So if I come here, that's, I don't know, probably about here, give or take. 95% of the area is to the right of that, right? Then, let's take another example real quick. 99% of the area is to the left of 2.088. So that's going to be a little further to the left. It's going to be over here somewhere, right? 95% of the area is in this piece. All right, so let me clean this up, and we'll see how we can use this to find the kinds of critical values we're going to need to create some confidence intervals. All right, so suppose we're looking at a sample. I'm sorry, let me get rid of this too. Suppose we're looking at a sample with 11 data values, and we want to construct a 90% confidence interval. All right, well, 11 means 11 minus 1, or 10 degrees of freedom. So my critical values are going to come from the bottom row here. Now, because we need to have 90% in our result, that means I need to find a lower bound and an upper bound. These may or may not be where they end up, so that 90% or 0.90 of the area is between them. Right, we're going to do the same kind of dance we've done with all of our other distributions, right? If 90% is in the middle, then the two outer tails must contain the remaining 10%. And just like with our previous calculations, I want it to be split evenly. I want to have 5% above and 5% below. Okay, now the 5% or 0.05 above is easy to find. I'm going to look at the 0.05 row and go down to the, the 0.05 column, go down to the 10 row, and I get 18.307, right? So this tells me, right, that if I say it wasn't too far off, let me amend my line here, get it over where it needs to be. Right, 18.07 is right around here. Right, that tells me that 5% or 0.05 of the area is above 18.307. Now, to find the lower value, we have to remember, we have to phrase our question in terms of the area to the right of this point, whatever it is. Right? Well, if there's 0.05 here to the left, that means there must be 0.95 to the right, and that's consistent, right? I know that this piece here is 0.9, and this piece here is 0.05, so together, they make up 0.95. Excellent. Now I'm going to go to the 0.95 column, go down to the 10 degrees of freedom row, and I get my second critical value, 3.94. Right now, the way I like to label these, I like to call this one chi-squared, and I put a little r down here because that's the right-hand critical value, and then over here I'll put chi-squared, and I'll put an L for the left-hand critical value. I like that it's descriptive. I immediately know which side I'm looking at. Some textbooks, they call this right-hand one chi-squared alpha over 2, right? Because alpha over 2 was 0.05. And they'll call this left-hand one chi-squared 1 minus alpha over 2. Yes. Okay, those are descriptive, I guess, but I like the L and the R, putting the alpha over 2. There's a lot going on down there now, especially with the left-hand one. I think it gets cluttered. And I like my calculations to be as mess-free as possible, right? So I'm going to use the L and the R, right, in all of my examples. Okay, now that we have our new distribution in hand, our next step will be to see exactly how we can actually use this to construct confidence intervals.